That's one of the interesting things that we're finding out, and we've been asking ourselves that universal question is, what's the general level of knowledge of hyperdimensional computing of people in the valley? People that actually should be aware of what this is and how it works. Because it's a very subtle type of algebra. And this is the first algebra that I've ever seen that started a completely different form of computation. And the form of computation is based upon objects, generality, similarity, associativity. Let's see, what are some of the other, human brain. How does the human brain work? Does anybody have a glimmer of what type of memory the human brain uses? One form that you learn in school is auto-associative. And the auto-associative characteristic is that you see a logo, for instance, and you know that that's Ford. It doesn't say Ford, it's a logo. You see a swoosh, and you know it's Nike. What's happening here is that triggers an association in the brain. That part of the brain is called the new brain, or the neocortex. The neocortex is a growth that came out of the old brain, and the old brain is also known as the reptilian complex. And as we'll see in the lecture here, you'll see how that dividing has happened over hundreds of millions of years. So we just didn't happen on the planet. It was developed from a very, very long program, if you will. So with that, let's pop into where we're going. Notice that Max Planck said this, and he was a very subtle guy. There are tribes of belief within any organization. And we have this ability, because of our neocortex, to form these tribes. And of course, the following becomes very strong. And we even have a fiction called governments. And we feel very strongly about division in governments and things like that. And we're still moving along those lines, as we have been able to see in the local news feeds. The other one is science advances on, where are we here? Here it is. Randomness. I love this quote. This is from Pentti Kanerva. We'll talk about Pentti a little bit more. He's my local hero here, and I like this guy. He's a hardanger. Who knows what a hardanger is? Well, see, homework already. Randomness is the path of least presumption. And that's one of the more beautiful things that I've discovered in this research. Machine learning is not intelligence. Do I have to yell louder? This is one thing I have to tell you, it ain't intelligence. And we're finding out the hard way. Well, this is what we've learned so far. It's not saying that deep learning is bad. It has a lot of promise, and we're going to use it a lot because the real thing that we're after here is artificial general intelligence. We're not after the bits and pieces. We want to take a look at the big picture here. It's entered the Gartner trough of disillusionment, where people are finding out it's got real limitations. And that you can't do the types of things that you need to do to go AGI. Sequences, A, then B, then C, then D, are very important. In fact, they're mandatory. And it requires hierarchical temporal memory. How many people are familiar with HTM? Good. Because you're going to see a lot more of it as time goes on. Prediction, absolutely necessary. Without prediction, we're not going to get there because this is what your brain, my brain, everybody's brain does. We predict all the time. You ever watched Steph Curry in warm-up with the basketball? You ever watch him? That guy is training, all right, his brain, his neurons, his connections to making that ball go through that hoop. And you have to be there and watch Steph do the practice to understand how much he is concentrating on making that ball do its thing. It's really rather amazing when you analyze what he's doing. And that physical capability of placing that ball in that hoop is really an amazing computational capability, bar none. And it takes lots of coordinated predictions in order to make that sensor network work properly in order to make that ball go through the hoop or do a swish. Fast learning required for anomalous conditions. What happens when you run off of the road that Google was preparing for you or had stored for you? It's a new condition. Or they did something that's not on the map. You need to have a quick learn. And when we run off into a new street or a new neighborhood, we're on a gimbal. We're basically in combat with our conditions because we don't know where we are. Thalamus is the center of that. It's in the center of the brain that's responsible for that. But the interesting part is all of these pieces work together within the brain. They communicate. Now, one of the strange things that we're still have a problem with is there's no real signal that travels through the entire brain, which is pretty interesting. And that's still a question that's left to discovery. I think Numenta, of all the institutions I know of, is probably closer to understanding that, along with the Redwood Neuroscience Institute at Berkeley. Those are one and almost the same as far as talking about one another. Fast learning, whoops, I went which way? Fast learning required for anomalous. The broad span solution, what do I mean by that? I mean, it's got to go from embedded controllers through high performance. We're talking Internet of Things, IoT. This is going to become extremely important IoT. Later on in the presentation, you'll see that people are already making silicon for this stuff. So this is not, an over the horizon. This is stuff that's actually going into 5th generation phones. Did I say 5th generation phones? Yes, I did. Talk to the people at UCSD that are connected with Qualcomm. Well, maybe that's not such a good connection nowadays, but it's definitely improved. But the guys at UCSD, guess who they're connected to? Berkeley. Yeah. Stanford's a wannabe, but they're coming up fast. Yeah, this is wildfire now across the bay. And the cognitive database capabilities. Forget me not, cognitive databases are going to be a big thing because of the hypervector requirements. And how we handle hypervectors through graph analytics, even bigger. Let's take a look at the new versus old brain. In the beginning, there was sponges and jellyfish and things that were, and flatworms, et cetera, that didn't have much intelligence. Their nervous system was, ouch, don't do that. Or that's hot, that doesn't feel good, move. It was that type of a decision making. So we are talking about an instinctual type of brain. And that basically stayed in stasis almost up until the end of the dinosaurs. In fact, it was after the end of the dinosaurs that the new brain reasoning came in the form of primates and whales and dolphins. And one of the interesting stories that I stole this foil from Scott Phoenix. He's the CEO of Vicarious AI, located in Union City, right next to the BART station. Oh, Good, we got transportation now. 2, the houses are lower cost, all right? It's everything the peninsula ain't. So there's going to be a huge amount of growth over on that side of the bay. And I can almost walk there from my house, as a matter of fact. It's that, I ride a bike there easily. But Scott is, Vicarious is the darling of the venture capital groups right now. They just can't get enough of these guys. And they're in robotics. And he's on YouTube. If you go on YouTube, Scott Phoenix, Vicarious, you'll get he's very good on screen presence, very good. But Scott's from Numenta. Do we see a lineage here? Yeah. We follow lineages because we know who talks amongst themselves generally follow the same rules because they're a tribe. Very simply. Some are tight, some are not so tight. But we know this all from our everyday commerce and people in our daily lives. That's the way humans are. So we utilize that in our studies because it's extremely important when it comes to the transmission of complex ideas. The point here is, and he also makes the point where they had whales in a tank in one of these ocean world types of exhibitions, and whales, the orca whales, would bring up a dead, something that had fallen into the tank, and they would bring that up to the trainer, and the trainer would give them, instead of 1 fish, they would give them 2 fish. And the orca went and took one of the fish, put it at the bottom of the tank, and used that as bait to catch more seagulls, and drowned them and put them at the bottom of the tank. So he got more fish. And then he took those fish, all right, to show the other orcas how to get fish. That is absolutely astounding because that shows a lot of presence of artificial general intelligence right there. It's all around us. So one of the lovely things I've been doing all my life is watching animals very correctly. And anybody who says, well, they're just animals, you want to knock them in the head because that ain't true. They're very intelligent. The old brain is stimulus, instinct, and response. There's the picture of the bug crawling up the iPhone screen, and there's the toad sitting there popping the tongue out to get the bug off the screen. And when they touch the screen, the bug goes away. So that is basically the input and the feedback response to the toad. They'll starve to death. They'll just sit before that phone, popping their tongue on it all day long. That's also from Vicarious's presentation. Low generalization or no generalization. Good at high probability inference. When you really want to examine something under the microscope, this one is where you go to get the 97.9 to 98.6 classification probabilities. So we will be using it a lot because there's conditions where you want that much surety on your inference. It requires a large amount. This is the real bummer. Did you hear the story about the interns at Google who spent $250,000 of electricity tuning? Yeah. This is not good. Cost of ownership probably is not what one would want long term. It's the old, we've got an artificial, we have an intelligent automobile, runs off of batteries, but it can't make LA because it doesn't have enough juice to run its artificial intelligence engine. So I'm sorry, Mr. Musk, we're just not going to make it. It's true though. It's DGX1, DGX2 from a very well-known company, NVIDIA. How much power does it take?
500.
No.
The whole thing?
Yeah, the whole thing. I'm talking about, you know, the GPU on a stick treatment, okay, that everybody's, even IBM is trying to use as their engine. Well, it's got a problem, and by the way, have you noticed that there's been a lot of muting of the wonders of deep learning lately? Have you wondered about that? Have you even noticed it? Well, one of the reasons that some people are saying that we're going into another artificial intelligence winter, and AI winter is that we have the hyping of a new technology. It appears to be successful. It spreads throughout the media. Everybody thinks that, oh, finally robots are here. And then we go over the hump and we find that it has problems, that it's not going to fulfill where we want to go with our science fiction fantasy magazines. So not being caught up in that is one of the problems that you need to understand, that there's always going to, the Gartner hype cycle is very true. And it's always good to go Gartner hype cycle and your year you're in right now to understand where they think particular technologies are going. And there's the valuation over time it's really pretty important function that Gartner has, and it's fully protected too on their IP. We looked into it because we're thinking about another one on how to do memory in a similar way. The problem that I think holds it back the most is you would like to have it like a projector. You would like to be, you know, telling me what's in my scene all the time. I would like to be turning that old-time crank on the cinema. And I would like to be spitting out, well, I'm seeing three people sitting in a lecture sitting, so on and so forth. So I would like it to be more general in its capability of output. Instead, it's just saying, I identify face. And it is not in my database. I identify face. It is not in my database. It's a very narrow, one-sided affair. I need something that's more general, its capability that tells me more about the scene that I'm looking at, even down to the nuts and bolts. So it becomes pretty obvious that one of the things that I'm looking at is I want to identify objects. And once I identify objects, I also want to identify further down in the tree structure of what makes up those objects. Hair, coat, pants, underwear. I want all that stuff. I want to be able to go and get it. And that's where the cognizant object database treatment with the graph analytics comes in here. And you can't adapt this to that. And that's what where the DL is not adaptable. You can do anything given enough time. But knowing deadlines, you have to get it done in order to make return on investment. The brittle failure modes, we had Uber in one of those. That was a brittle failure mode. It killed a human being. They're now rethinking their technology tracks. Now, do you think Jensen Huang is talking about this? Yeah, he's talking about it. The new brain is hyperdimensional computing. And you'll hear Vicarious talk about new brain. And the reason they're not telling you what the new brain is it's based upon hyperdimensional computing. And we'll talk about that in a few seconds here. It relates human intelligence, the properties of human intelligence, the way we actually think, to abstract mathematic spaces. In other words, we're talking about an algebra, and it's a proved algebra. It's a closed algebra. How many of you guys took advanced field theory in mathematics? Ha! I almost flunked it twice. It was very, very, very rough. It's just proof after proof after proof. It's just like, I never want to see another proof in my life. But it's that's the beauty of what Penty is done here. This is a real jewel of applied mathematics. And don't ever say I said applied. It's a dirty word amongst theorists. All right? You don't get there. It associates patterns and analogies. Oh my, analogies? How much of what we learn is by analogy? It's just about everything that we learn. It's when we say, well, 85% is vision. That's what we learn by. Well, the vision is interpreted by analogy. I have to go look and associate everything in the scene. What if and why? Single pass training. Yeah, single pass. No tens of millions of reading those numbers. My range of applicability from toys to supercomputers. So if we're going to get this stuff made in the semiconductor segment, you're going to have a wide range of applicability. Otherwise, they won't do it because they won't see the ability to fill up their factories. Remember, a factory isn't run on a whiz popper, it goes bang. It's run on the money I invested and the money I can sell and what my average sales price is, and then how much of that sales price is a percentage of profit. So they don't care. They want to know how much money they can make. And it can predict probable outcomes. This is probably the most succinct advantage it has, because we, as humans, if you read on intelligence, which I'm going to have up here, you'll realize that our brain is incessantly predicting action. We are prediction machines. Artificial networks, DL just blew everybody else away. We could talk about nothing else in artificial intelligence for almost a decade since Geoffrey Hinton broke out with deep learning from the University of Toronto. We've just nothing else. And the solution has been to make arrays of multiply accumulator MAC solutions with data highways in between them to do the weights communication. The memory use in these is external. It's external. That's the one thing we have to remember. It has no external object association tether. That's the biggest weakness of this algorithm, is that it's its weakest link. It's beautiful for what it does, but trying to get to the next step of artificial general intelligence, it's not going to make it. A hyperdimensional computing effect is really rather subtle. It requires an overlay of cognitive object database, like I've been harping on. It's a node as an object and a vector edge represent either the Hamming distance in the sparse dimensional memory, or it represents the cosine overlap in the hierarchical temporal sparse distributed representation, or the cosine function, to the nearest and farthest relations between hypervectors. So those objects are hypervectors, and I'm measuring how similar they are. Vector relationships are being incorporated in the cognitive object database and probabilistic language. Now, I've got to back up here because I have missed a very important slide. That I'm going to play this for you.
Hi, I'm Daniel.
Hi, I'm Martin.
Hi, I'm Fernanda.
Hi, I'm Daniel.
Hi, I'm Martin.
Hi, I'm Fernanda. Machine learning is pretty complex, so we've been experimenting with ways to visualize what's happening. There's a core concept in machine learning called high-dimensional space. Here's one way to wrap your head around this concept. You can think about people as being high-dimensional. For example, take famous scientists. You can think about when they were born, where they were born, their fields of study. Each of these is like a dimension of that person. These dimensions become difficult to untangle when you think about different people, because someone might be similar in some ways, but very different in others.
But this is the kind of thing you can use machine learning for. With machine learning, the computer isn't told the meaning of these dimensions, it just sees them as numbers. And it sees each set of numbers as a data point. But by looking across all of these dimensions at once, it's able to place related points closer together in high-dimensional space.
Here's a concrete example where words are treated as high-dimensional data points. The important thing to remember is that we haven't told the computer the meaning of words. Instead, we've shown it millions of sentences as examples of how words get used. Here's a visualization of the results. We're looking at a subset of words that the computer has learned about. Each dot represents one word. Each word is a data point with 200 dimensions. Using a technique called t-SNE, the computer clusters words together that it considers related, and clusters form based on meaning, even though we've never taught it the meaning of words. Here is a cluster of numbers, months of the year, words related to space, people's names, cities, and so on.
We can also look closely at smaller sets of words. If we search piano, we can run t-SNE only on words related to piano. We get clusters of composers, genres, musical instruments, and more.
And this approach doesn't just work for words. For example, you can also treat an image as a high-dimensional data point. Here's a data set where lots of people wrote digits between 0 and 9. People write in all kinds of ways. So the question is, instead of us needing to manually code rules for all the ways people write, could a machine figure it out itself using machine learning? Each image is 784 pixels. The computer treats each pixel as a dimension. Again, using t-SNE, it clusters these images in a high-dimensional space. We've color-coded them so that it's easier for us to see what's going on. And you can see groups of digits clustering together. It's learned something about the meaning of these digits.
These visualization techniques we've been exploring can be useful for all kinds of things. That's why we're working on open sourcing all of this as part of TensorFlow, so that anyone can use these tools to explore their data.
I use this because it's such a well-produced item from Google, and because it's open source, I can use it. The really interesting part is that, did you notice the grouping? It's t-SNE, actually that was University of Maastricht in Holland. I actually have one of our colleagues in this research did a lot of the work in that. And it just happens that he has other interests, and it's in fine art, and he's actually retouched. He's used by the Rijksmuseum in Holland to restore famous painters' pictures in oil. So he's touched Rubens, he's touched these masterpieces. He's actually done the restore on it. But he's a theoretical mathematician. It's a great guy to know, actually. And they're the ones that are actually running hyperdimensional computing in simulation right now. And their firm is in competition with a lot of the spook firms who do information gathering for governments, et cetera. Let's talk about Pentti Kanerva. Pentti came in 1967, started to work at NASA Ames and on the brain, especially the language. Now, one thing that you have to understand is that language is a good place to start when you're looking at the brain, because it's one of the ways that we express ourselves comes from the way we actually are living in our thought processes in our mind. And because it is in words, etc., Penty decided that it would be good to look at words, letters, trigrams. Who knows what a trigram is? Bigram? Good. It's used a lot in the industry of when you're trying to break codes, because regularity and sequence of words will stand out over time. As you saw in the video, certain words tend to be used more than other words, and that's one of the epitome concepts of code breaking. So he started this investigation. In 1988, he wrote this book, and this is a jewel of a book. This is the least waste of paper I have ever seen in my life. This is a nerd's book, all right, because every page needs to be there. It's that full. It's really a great book, and I recommend it to anybody that wants to get into hyperdimensional computing. This will take you there. We'll talk a little bit about how he set this down. He's at Redwood Institute now in Berkeley. This is the other guy, Jeff Hawkins. He was the founder of Handspring, became Palm. I call him the inventor of the iPhone, actually, because everything he did was basically in the iPhone. Steve Jobs basically just lifted everything. He's also, after he sold the companies, he and Donna Dubinsky co-founded Redwood Neuroscience Institute, RNI, in Redwood City, and that was 2002. When he formed Numenta, he gifted RNI to Berkeley, the University of Berkeley, and it became the Redwood Neuroscience Theoretical Institute. And there's a lot of really good, if some of the YouTube videos that are coming out of that, you realize that the room is full of the core people that are engaging in hyperdimensional research, and that it's akin to another project that happened there in the 1940s called the Manhattan Project. There's not a whole lot of people that are making this go. That's the other fact is that maybe a limitation is because they've got so much on their plate already, they don't have time to get out and do any of this type of proselytizing. I advise you to read this book. On intelligence, when Jeff, he worked for Intel, by the way. Does that give everybody a hint of what things are to come? In that Intel is a big supporter of the institute where Penty is right now. Quiet. Isn't that interesting? And you'll also see something that has 4 layers. Not 2, 4. Let's take a look. This is on off of El Camino Real, 2002. What we have here is Penty is in the middle there, smiling out at us. I think he's a Hardanger violinist. Anybody know what a Hardanger violin is? God, you don't know music. That's Jeff Hawkins in the middle. And there's Bruno. And Bruno's the head director of the RNI at Berkeley. And over here, we've got Dilip George. He's co-founder of Vicarious AI and co-founder and CTO Numenta. Do we see some entwining things going on here? Isn't it interesting? There's a lineage here. There's Scott Phoenix, CEO, he was formerly of, he wasn't in the earlier picture, he joined later at Numenta, but there he is smiling out at you in the second story of the building they're in right now. No, this is actually, this is Redwood City. They shared quarters with Numenta for a while. And there's Dileep, all right, he's the CTO and co-founder with George. And these guys attracted $120 million from Peninsula money. Let's talk about congestion. This is where the rubber meets the road, so to speak, is that we have the future of computing is rather uninspiring at first glance. And then once you get down into it, there's lots of attitude here. The latitude is actually so vast that it may be difficult to get your arms around it. We have Moore's Law, we have memory wall, we have the heat wall. They're all standing in front of CMOS, CPU, GPU, engines, if you will. They're looking at better memory storage, bio-inspired computing, memory computing, and cognitive, big data, Internet of Things. Notice that cognitive computing can reduce the amount of big data by probably at least half. People are afraid to throw away data now, so that's what has spurred the sales of solid-state disks. Hey, it may be important, we don't know. All right, so there's that. What we're also seeing is that we're seeing, more importantly, is this fine-grained integration in 3 dimensions. This is going to, as you'll see a little bit later, this is really an important important idea here that we're going to put all these architectures into. And of course, we have the device properties themselves. We're looking at a memory processing unit. This is the interesting part, is that this is the Grail. Perform different tasks, data, storage, arithmetic, logic, and fabric that is programmable at the finest grain. The individual device level without the need to move data outside the fabric. Now, this is HTC. Notice I have the application, which consists of letters, image, features, phonemes, DNA motifs. They're projected into hyperspace by a multiply. That multiply happens to be a exclusive OR. Also notice that those hyperdimensional vectors are 10,000 bits, but they can be smaller, but 10,000 bits. In fact, in order to do prediction, we may need as many as 20,000. And I'm talking about a multi-framed prediction. The map kernels are multiplication, addition, permutation. And multiplication is an exclusive OR multiply. It's not a multiply, not a data tree type multiply, not a floating point, not even, it's just a plain exclusive OR. Addition is an OR, and permutation is just a right or a left shift, mostly a right shift. That's the operands. Very simple operands. And that is the computation units, which turn out a hypervector, which then is compared to all the others. That's the associative engine. Very simply, that's the engine that gives us hyperdimensional computing. In a block diagram, simple. We have motor sensory input, as I said, less than 10K or less. The encoder unit, which is the multiply. And the associative memory processor is approximately less than 4 terabytes. And that's the Hamming distance difference between hypervectors. If you look at the hypervector space, address space, it's 2 to the 10,000, which represents that exponent 3010. So is that big enough to be random? I figured, yeah, that's way bigger than you want. So evidently, what we're doing is we're mapping into hyperdimensional space. associative memory processor training plus experiential is going to be somewhere around 4 terabytes. We're looking at leverage the unique structure and properties of VRAM. Map kernels demonstrated on 4-layer vertical resistive RAMs. And we're looking at in-memory high-dimensional computing enabled in a 3D architecture. And this is, there. Multiplication shows the 4 layers. Remember I was telling you the 4 layers? What non-volatile memory has 4 layers in it now? Thank you. Yes, it's Crosspoint. It came out at 2, but it went to 4. How is that? Ever wonder what's underneath that heatsink? Oh, let's remember. Who supports Berkeley? Addition. Permutation. What did Intel just announce? The data flow machine. So we'll give you a little clue about investment. May 2019. Yeah, those are approximate announcement dates. Supercomputer is in Frankfurt this year. See, they're human. They always work on clocks. It's in your thalamus, by the way. Go study. Yeah, I know. What was the number of the one machine that they put out that everybody liked and then they killed it because they couldn't make it? Yeah, I've been there. We're talking about non-volatile, and we're talking about NVRAM, which is another name for Crosspoint. Or everybody's working on that right now, by the way. They haven't announced it, but this is what the world is working. The first number, unlike low latency at 13.5, is NVRAM. The other one is called NRAM by Nantero. And I was very anti-Nantero at the beginning because every time they ran out of money, DARPA always kicked in more and they kept on going. So what could I say? But Greg Schmergel and crew were able to make what's become a darling. And as Nicholas Taleb says in his book, The Black Swan, is that the best thing you can do is just, as a developer, is to just keep on working and hope you have the good luck of running into a black swan that can use what you've been doing. He says, because all the great inventions have been black swans. You can't plan them, they just happen. And so corporations that are saying that they are going to invent the future of artificial intelligence are probably not going to be here in 10 years because they're starting off on the wrong way of thinking about it. Is that, yeah, you're going to fail a lot going there. So I think that's what's happened to Nantero, and their devices have a 300-year retentivity. I kind of like that, all right? I could put my brain into that and be kind of dependable that I'd be around in 300 years. Well, at least that part of me. The endurance is 10 to the 15th, so notice it's not as big as a DRAM, but it is sufficiently large. And also they can build layers. And also they were in part of a test run at Stanford, and they were able to lay out Nantero's devices on it. They will be in production of engineering samples from Fujitsu in, say, March or April of next year. So this is near term. This is, and the stuff works. And they've gotten it's actually spin the nanotubes in a slurry on the wafer. So it's pretty cheap stuff, actually. And we like it because it's fast. This How's this thing work anyway? Oh. This 4 layers, that's mandatory. No refresh, it's gone. Persistence 300, and the access time is 5 nanoseconds. And the power is less than, I think it's 6.5 picojoules or something like that. It's very small. This is more properties of the hyperdimensional that we've pretty much already dwelled on. Training sets. Because of the one shot and the quick learning, your training sets go from, like this, down to the dot in the eye. It's amazing how much reduced. And you maintain your classification capability. That's a big deal as it works out. It's a memory-centric architecture with significantly parallelizable operations. And what we've just shown is parallelization of the hyperdimensional memory compute. Extremely robust against most failure mechanisms and noise. You're going to hear the word holographic memory a lot, and that means it's what I call, it can be battle damage and it keeps on operating. That's, military loves these things. Predictive analytics with high accuracy, easily incorporated. We've already seen, can't say who the company is or what they're doing, but we already know they've communicated their progress. We think it's the associative-based technology for the cognitive software pyramid. We think there's the rest of the HTM, by the way, Numenta, is built on top of this. We think this is the bottom core calculator. And notice that multiply, add, P, all goes into, you can use that as a kernel. You can use different formats of that in order to do different algorithms. And believe it or not, it's an amazing amount of things you can do with just those 3 items. There's also a paper called Ambit, and that Ambit paper was done by NVIDIA, so on and so forth. And it's bitwise operation within a DRAM. And it's akin to something I did, because I got some calls. I did a hyper search DRAM back in 2006 along these same lines, because search operations are really what we're doing. And we're doing them on a bit basis here, and we're doing them on gigabytes per operation. So you can go take the back of the envelope and figure out how many operations that is per second. It's tremendously large. This shows you that we have silicon now. This was in memory learning. This is ISSCC this year, January. We'll have, you see they have already laid it out. They've already had silicon, working silicon. You have to have working silicon to make the solid states conference. Notice that we have the encoder of the sequence, and we have the resistive RAM-based classifier, which gives you the output of the Hamming distance. And this is also another dual classifier showing the actual logic circuitry. This is the brain-inspired dimensional of ultra-low power platform. This is done, it's called Pulp HD, high dimensional. It was done by the University of California, San Diego. And I think this was to help out their friends at, what's that company that's suing everybody now? Qualcomm. It's a 4-core ARM, and it's 1.5 millimeters squared by 2 milliwatts. Remember what I was saying about toys to supercomputers? Now to the important stuff. This is a DIMM. It's got a lot of persistent DRAM on it. It also has some FPGAs, and it's a form factor. You can put it in your memory channel. And here's what it looks like. Is you have this Intel Xeon there with this FPGA hypervector encoder engine, and it goes to your non-volatile DIMMs on the memory channel. This is the analytic grouping. It only has one analytical processor on it. That's the blue dim on the back side. This is a way of entering at low cost hyperdimensional computing acceleration. This is the Canerva partition. It's the real-time predictive analytics capability. And what this does is this provides you with the real-time analytics on your in-memory database. And notice it isn't, this isn't a DGX2 at $700,000, and you can own it and not have PG&E, put another meter in. It's really expensive. This is in the works. So we'll be able to have this experimental apparatus probably within the next year or 2 years. I think it's about a year away because it's getting actually getting the FPGA right on the DIMM to do the encoding and to do the search. Is it slower? Yeah, sure it is. There's a lot of better ways to doing it. But in order to get the market started, it's a way to cold start the ability to start fooling around, if you will. There's going to be a lot of that to make this all work. We're going to have to learn the whole genre of people in the art. That's it for us. That's WebFeet Research, Alan Diebel and myself, Gil Russell. There's Alan, be reached there, and I can be reached there. And notice one thing. Big problems for nervous tissue. In case you didn't know that, that's you. Thank you for your time, and I'll open it up to questions.
Question. Can I go back to the slides?
This one?
Who's doing this? Are you doing this, or are you working with somebody to build this thing?
It's a Silicon Valley thing. We're talking everybody into it.
So you're trying to persuade someone to build
Yeah, we got some guys in LA that are good at doing modules, building those. We have some people who've done a huge amount of work for Intel on FPGAs. You got to know who your friends are on these types of projects. Yeah, it's open right now. We're borrowing things from GitHub and everything else, all right? Because don't reinvent it, patch it together. We don't have enough time to screw around with development. We need to, most of all this, by the way, you can go to GitHub and find out all the little treasures that are there. It takes a little time, but it's well worth the effort.
What's that HB encoder? What is that?
Hypervector encoder, yeah.
How many encoder doesn't is it take input to put in the certain format or something?
No, it has to be less than 10K bits. A hypervector can consist of anything you want, and that's one of the issues is how you label it. All right. The IID nature of a hypervector means that you can put anything in there, but if it doesn't have a relation to the other hypervectors, it's not going to show up as an association, or it will be more distant.
So what's the function of this encoder? For example, let's just give you an example. Somebody give you a book.
Yeah, if you look at Canerva's 2009 paper, Penti-Canerva 2009 is what you want. He demonstrates the arithmetic.
No. I mean, what this encoder does. So it's basically, for example, I take a book. This one encoder each word generate a random bits that represent a certain word. Well, I mean, I just want to know what the encoder does.
Oh, it actually encodes the hypervectors. It takes the bits, which are here. It's right here. All right. This is the motor sensory input preprocessor, and it feeds into the hypervector. generally what it's doing is this is going to strip down the bits into an integer type code.
So you take the input from
Right, and this comes in as a sequence. It can be a lot of different things. It can be a sequence. It can be genetic, literal. It comes from your own code and what you want to have as your associative memory. In other words, if you want to have a large database and you want to associate it, you have a lot of small bits of genetic material that you want to be able to more quickly associate with one another, then that's what you're going to encode.
So that one's basically code based, take the input and generate.
It's very simple. It just makes 10,000 vectors. It fills in the zeros. This is, did I tell you it's sparse? There's a lot of zeros. Well, that's also what this does. It takes the zeros down. So if you have a zero removal compression, if you will, you can actually keep that. It doesn't work as well, but it will still work as far as measuring distance, Hamming distance between it, even though it's compressed. So this takes a lot of the functional energy out of the equation.
Thank you.
You're welcome.
Yeah, it just reminds me of like the connection machines in the 80s, right? So some of that specified.
Thank you. Absolutely correct.
So Danny Hillis did some of that work, and I'm just curious, do you foresee some of this going too specialized of a hardware to actually hit mainstream, or what's your sense of the promise, actually?
People that have been in the business long enough to remember the connection machine tombstone, as we call it now, make that remark. Yeah, they said this looks like the connection machine a lot. And yeah, they're right, it is. What is Hiddleston doing?
I think last year he was advisor at Walt Disney. I mean, I haven't lost track.
In fact, Danny would probably love this thing, all right, would be my guess. It's been a long time since I went to the old Oyster House in Boston.
So how about IBM cognitive computing? So what?
To what type of computing?
Cognitive computing.
Cognitive?
Yeah.
Absolutely one and only, yeah. This is one and onto. This is, you can take entire volumes of books and make those into cognitive entities or hypervector sets.
It's very.
And you can compare one paper to another paper.
Yes.
And what blew my mind was someone wrote, the guys in Holland wrote, they took 10 different papers and rewrote it. And the rewritten paper is really good. And I said, now that's something I could use. How many of you guys could, take the 10 best papers in the world and make the very best paper in the world in your research? Yeah, I know. I felt small. I said, I'm replaced. But that's an idea of its use. That's virtually possible now. Yeah, once you get hold of this thing, you cannot put it down. You'll wake up in the morning and say, I could do this. See, what it sets in motion is your heteroassociative memory, which is this is what that is. The ability to take small sets of other things and to relate them and associate them together. This is a very powerful tool. In fact, this is the most powerful tool I think I've ever seen. And I like forging sharp edges. And I admire samurai blades. This is really a very interesting, this is the most interesting thing I have ever worked on. And it's hard to put down. I guarantee you, once you start into this stuff, you won't get out. The rest of it is fluff. It's, yeah. In fact, do you remember the hyperdimensional product of the 11-dimension physics problem? This makes it nearer. Because you can now take and associate Think of the Hadron Heavy Particle Accelerator in Switzerland. All right, and they have to look at the tracks and everything, and they're trying to associate those with other particles. This thing, all right, can take that thing apart and run it in a few minutes. The time crush of this ability is absolutely astounding. Oh, the silicon I showed you, all right, it all works. It's already going, they're planning to use this in the 6th generation, and now they've decided to put it in the 5th generation, because they're going to start taking the phonemes of our voices and encoding that, because they can use less bandwidth. And they can also use identification because of the phoneme structure. That little item had actually 2 engines in it. One was a phoneme structure, and the other one was a compression structure. And both of them based on hyperdimensional computing. The other thing I didn't say, and I should add, this is why China is so preoccupied with vertical resistive RAM. 4 layers. 4 layers. See? I've given you a hetero-associative clue to look for now. 4 layers. All right. Thank you. I think we're at an end. Thank you.